So here's an example of course, if we look at the standard deviation 1 and 2 of a standard normal, there's a certain amount that corresponds to a certain percentile. If you go from -1 to +1, right? So each one, so this is minus sigma plus sigma, each one of those points corresponds to a specific percentile. And here what the author has done is use the z-value of plus and minus 1 to get stock prices in one day. So in this example, we start with a stock price of 50. We're assuming a 15% real-world return annual, no dividends, and a 30% standard deviation, a 30% volatility. And with those parameters, we can get for different t-values, and you would measure everything in years. So a month, these are the t-values. Everything's expressed in a year. A day is 1 over 365, or 0.0027. A month is 1 over 12, or 0.0849, and so forth. And so what we see is that with those t-values and our earlier formula, here we're using the plus and minus sigma and 2 sigma. These are z-values, and what we would need to do is to say what confidence interval does, for example, if I look at 1-year prices, 41.14 to 74.97. Well, that's a confidence interval in stock prices at time 1 year corresponding to the normal confidence interval from minus to plus 1 standard deviation. And that's a confidence interval that has probability is at 65%. I'm forgetting now exactly what that value is. But you see that you can work either way. In the prior slide, we identify the confidence we want, and we can then identify the z percentile that gives it to us. Or you can use these formulas in terms of looking at the various confidence intervals of the normal and mapping them into the confidence intervals for z. So plus or minus 1 sigma in the normal, the probability of that is the same as the probability of stock prices being in the stock interval that is derived with those z values, right? These are all z values, plus 1, minus 1, and so forth. So just graphically, what we're saying is that we have our standard normal distribution, and it has a sigma of 1, and 65% or so of the total mass is in there. And we then have a log normal distribution, which is has a skewness to it. And what we're saying is that 1 for 1, every percentile of this normal, so if I go here and I pick off the z 0.025, the 2.5 percentile of the normal distribution, it's the value of z for which there's 2.5% probability mass to the left, 97.5 to the right. That z value, through our earlier formula, gets mapped to the same percentile of stock prices. And correspondingly, if I had the 90th percentile of the normal distribution, that's the value where I have 10% above it, 90% below it, that z value in our formula gets mapped to the stock value, which is also the 90th percentile. So percentile by percentile, each of the standard normals gets mapped to the percentiles of the log normal distribution for S using that earlier formula. And we can do the same thing with, here we have plus or minus 1 sigma. We could map those. So this might, this value, so this would correspond to a z of minus 1. This would correspond to a z of plus 1. And this interval has exactly the same probability for capturing a stock price at this time as the interval in the standard normal has of capturing a standard normal variable, identical. Okay, so it's quite easy to go back and forth. So let's return to the log normal density function. We developed the formula for the log normal density function for general y, and it's good to just be a little more specific of what does the log normal density function look like for ST. ST is log normal, and so recall, so S0 is our typical initial price. We're assuming that the continuous return from time t to time 0, which is the log ratio, that continuous return is normally distributed, all the usual parameters. Notice I'm using alpha here, so it's a real-world model. So I can just by taking the log of the ratio as a difference of logs, I can add the log of S0 to the right-hand side, and I'm shifting the mean. What it's saying is that the log of ST is normally distributed. The log of prices at time t has a normal distribution with a shifted mean. Namely, it reflects the log of the initial price. It then reflects the parameters of the model. So ST, because, and this is identical to, I think it was slide 1820, we derived the same formula. This is the derivation that ST is log normally distributed because its log, the log of ST, is normally distributed.